Welcome to Module 1 of Well Testing and Analysis 2. In this session, we will dive deeply into fractured reservoirs, flow behavior, fracture detection, and the foundational approaches to evaluating such reservoirs using conventional methods. We will then move on to a detailed discussion of type curves, setting the stage for more advanced topics in Module 2. Let's begin by reminding ourselves of the role of well testing. In petroleum engineering, well testing is not merely about measuring flow rates or pressures. It's about interpreting these measurements to extract information about the reservoir's capacity, structure, and connectivity. When the reservoir in question is fractured, either naturally or artificially, the dynamics of fluid flow become far more complex. Understanding these complexities is essential for accurate reservoir characterization and effective production planning. 1. Understanding fractured reservoirs. A fractured reservoir is a hydrocarbon-bearing formation where a significant portion of the fluid flow occurs through a network of cracks, fissures, or fractures in the rock. These fractures can be natural fractures, formed by geological processes such as tectonic stresses, folding, and faulting. Induced fractures, created during hydraulic fracturing operations to enhance well productivity. In a fractured reservoir, the rock matrix and the fracture network together control fluid storage and movement. The matrix typically holds most of the hydrocarbons due to its pore space, while the fractures provide the primary pathways for rapid fluid flow. Why fractures matter in well testing? When a well intersects a fracture system, early time pressure behavior is often dominated by the high conductivity pathways, while later time behavior may reflect the slower exchange of fluids between the matrix and the fractures. Misinterpreting this can lead to overestimating reservoir permeability or underestimating reserves. 2. Flow behavior in fractured reservoirs. Flow in fractured reservoirs is typically conceptualized in dual porosity or dual permeability models. In dual porosity systems, the fractures provide high permeability conduits, while the matrix provides storage. Fluids move from the matrix into fractures and then toward the well. In dual permeability systems, both the matrix and fractures conduct flow, though at different rates. Key flow regimes to recognize. Bilinear flow, often seen in hydraulically fractured wells, where fluid first flows linearly through the fracture and then into the reservoir matrix. Linear flow, common in high conductivity fractures, showing a straight line trend on log-log plots at early times. Interporosity flow, the transition period when fluid is moving from the matrix blocks into the fractures. This can create a characteristic sag or dip in the derivative curve during pressure transient analysis. Boundary-dominated flow occurs when the reservoir limits start to affect the pressure response, giving information about reservoir size and shape. Practical example, in a carbonate reservoir with natural fractures, early production rates might be high due to fracture conductivity, but decline steeply as the fractures deplete and matrix contribution takes over. 3. Fracture detection in well testing. Detecting fractures through well testing relies on identifying distinctive flow patterns in pressure and rate data. Indicators include early time linear flow, a strong early time slope indicating fracture dominance. Transition zones, a pronounced dip in the pressure derivative curve, suggesting matrix to fracture flow. Unusually high apparent permeability, early time interpretation that suggests higher permeability than later time data supports. Other supportive detection techniques. Image logs from downhole tools, showing fracture orientation and density. Production logging tools, to identify zones contributing most flow. Tracer test, which can highlight rapid pathways between wells. Fracture detection is not about a single diagnostic method, rather, it's the synthesis of well test interpretation, geological knowledge, and supporting data. 4. Conventional evaluation methods. Even with complex fractured systems, conventional well testing approaches remain the foundation of analysis. This involves running drawdown tests, where the well is produced at a constant rate and the pressure decline is recorded. Conducting build-up tests, where the well is shut in and the pressure recovery is monitored. Applying semi-log straight-line analysis to determine transmissibility and skin. In fractured reservoirs, conventional methods are still applicable but require adjustments. For example, in a dual porosity system, the straight-line method may yield a fracture permeability that does not reflect the matrix contribution, so we must interpret results in light of fracture flow regimes. 5. Type curves in fractured reservoir analysis. Type curves are graphical tools used to match field data against theoretical solutions of flow equations under various reservoir conditions. In fractured reservoirs, early time data matches with high conductivity fracture models. The middle time dip corresponds to interporosity flow parameters. Late time matching reflects boundary effects. Matching involves shifting the measured pressure and derivative data on log-log plots until they align with a theoretical type curve. This alignment allows us to read off parameters such as fracture storage coefficient, interporosity flow parameter, and effective permeability. In this first module, we've built a deep understanding of fractured reservoirs, what they are, how they behave, and how to detect and evaluate them using both conventional methods and type curve matching. As we move into Module 2, we will apply these principles to specific well testing situations from injection well analysis to gas well testing and horizontal well analysis and explore how advanced methods and equipment refine our understanding of reservoir performance.